Welcome to the video for the second problem in the second exam. In this one, we deal with a composite section. So we need to transform it. We determine the centroid in this problem. Later on, we'll have to find the second moment of inertia and the actual stresses and strains. In this problem, we want to find the maximum stress and the maximum strain that this section experiences. But this composite section is made up of two materials, tin and brass, or two metals in whatever version of the test you had. They may or may not have had realistic Young's moduli, but it's a purely academic exercise, right? So we've got our sections right here. That's our real section. But if we're going to subject this to bending, and in this case, this bending that this is going to be experiencing is 30 kip inches, we're going to need to determine the transformed section as well. So to do that, we're going to need N. N is equal to the ratio of the Young's moduli. It doesn't really matter which one you put on top and which one you put on bottom, just so long as you transform the one that's on the bottom. Or the top. So we've got, let's put the brass on the top because that way we'll have a N of greater than 1. And the tin on the bottom. And that's going to give us that N is equal to 50,000 KSI. Sure. Divided by, there we go. 6,500 KSI, and that's going to give us 7.69 with no units because we're dividing KSI by KSI. Good. N does not have anything like that. So now when we look at our transformed section, the brass can be represented by tin if we use N. But of course there's going to be a lot more of it because the brass is substantially stiffer than the tin. So let's draw our transformed section. I'm not actually going to make the charts to scale. Right, this is not, there we go. So this is going to be 1 inch times 7.69, which is going to be 7.69 inches. That's not in inches. We only have it in inches because we multiplied it by this distance, which very conveniently is 1. This distance remains 1, and this distance remains 1 inch, and this distance remains 1 inch, okay? We can only, because we're looking at it bending about the z-axis, so bending about this way, we can't look at it and transform it by going vertically. That will change our centroid. That'll change our second moment of inertia. Don't do that. Only transform it horizontally, okay, to get the same effect as if we had this whole thing made out of tin to get the same effect of this. So now that we've got that, it should be pretty apparent that our centroid, our neutral axis, is not going to be right here, right? Can't be. No way. There's all this right here, and I didn't even draw it to scale. This is 7.7 inches. So that's truly massive compared to this. So we're going to have to find our centroid. We know how to do that. I'm going to call this top rectangle brass, because that's what it's made of. The transformed is tin, of course, and the bottom, tin. The area of the brass is going to be 7.69 inches times 1 inch, so 7.69. The area is going to be measured, of course, in square inches. The tin is just going to be 1 square inch. And the sum total will be 8.69. Y bar, let's take it from the bottom. Okay, let's take it from down here. If we do that, the brass, why not change to red? The brass will be at 1.5, right? The centroid of this is at 1 inch and another ½ inch. And that's in inches. And the centroid of the tin will be at 0.5 inches away from this point. And finding AY, which is in inches cubed, of course, we're going to end up with 11.54 and 1/2. The sum of these is 12.04. And so we can say that our centroid is equal to sum AY A, which is going to be 12.04 divided by 8.69. That's inches cubed. That's inches squared. This becomes inches 1.38 inches up from down here. So now we've got the centroid. We're going to need to find the second moment of inertia of the transformed section. We're going to have to use the transformed section to calculate the stresses and the strains.